So I was over there reading to the kindergarten kids, which I survived.
Good job.
Luckily.
But
Barely.
well, there was like actually 3 kindergarten classes in the same room, and the teacher was trying to get them. They weren't loud, but she was just trying to get them to settle. And I couldn't understand what she was saying at first. And then I finally said, "What are you telling your kids to do?" She goes, "Catch a bubble." And I said, "What?" She goes, "Yeah, like like catch a bubble. You go like, and then you have to hold the bubble in your mouth and so
Wait. You gotta do that one for the camera. It was up a little bit.
Is this like the method of shutting up children?
Yeah. So if I tell you all to catch a bubble, there you go. So that's what I'm referencing. Okay. All right. So today is
A good news day?
Please.
no.
Damn it!
But the assignment isn't bad. So
Bad news day.
today is the second to the last lecture I will give you, and that's on buoyancy. And the last lecture I'll give you is on fluids and pressure and that type of thing. So here's the story. This is on this purple sheet, okay, on this section where it says like mechanics and fluids. So down here at the bottom, so we've already talked about some of these. Density is mass divided by volume, is pressure is force divided by area.
Okay, can I see your paper first?
We'll deal with that second pressure equation.
Oh, okay.
This says
That's
P
fine.
naught plus rho GH. We'll deal with that one tomorrow. And then the same thing with that gauge pressure. So what we're dealing with today is this FB equals rho VG. It sounds like the name of the physics game. Yo, rho VG. So when you look at buoyancy, okay, and y'all are vaguely familiar with this concept. So for example, if I've got this Erlenmeyer flask,
It floats.
and in it I have tied a top of a pipette, and that's tied to a string. So why is the top of that pipette floating inside the water?
It's full of air. Air is less dense than water, so it wants to rise to the top.
Okay? So
Gravity.
gravity. We're going to talk about string. So if you look at this simple example, and there's 2 kind of things how this can play out.
Oh, we're gonna count
So
these.
inside that Erlenmeyer flask, and here's the stopper, and you've got a piece of string coming up tied to the pipette, okay? So there's 2 forces that are acting on the pipette, trying to hold it down. You have gravity pulling it down, and you also have the string. So you have tension in the string and the gravitational force trying to hold it down, okay? Which is why the string is tight. Working up against that is your buoyancy force. Now, here's the most common misconception that it happens with buoyancy force, okay? Buoyancy force itself is a fairly simple equation. It's rho VG. But that density value is the density of the fluid that is being displaced. It is not the density of the object, okay? So listen to me again. That density is not what the object is. It's the density of the fluid that's being displaced. So in this situation, if I want to calculate the density acting on that pipette, I would use the density of water because that's what's being displaced, okay? So if you look at the units, you got density kilograms per cubic meter. Volume has to be in cubic meters. Well, if I take density times volume, what am I going to get?
Just kilograms.
Kilograms, right? Mass. And then we're going to take mass and multiply that by G and get
More
force.
mass.
Newtons. More mass. Okay? So this is why this buoyancy works out. it's just rho VG. Rho V is just mass, mass times G, boom, there you go, okay? So here's an interesting idea. So I'm going to take this, right, and I'm going to move this very rapidly to my left, okay? Right? So I'm going to move this to my left. What's going to happen to the pipette on the inside? You have three options. Okay, so I'm going to move it this way. Option number one, it's just going to move with the flask, and it's just going to stay in the middle. Okay? Option two, it's going to move to my left, your right, or it's going to get left behind, a move to my right, which would be your left. Okay? Cohen.
I say a pipette moves to our right because the water's going to resist that change in motion more. So it's going to be pulled to the back more so than the pipette. So the pipette should go this way, is
Okay.
my guess.
Yeah, Sean? You're on that train? Colin?
As hesitant as I am to
Follow
be a
Kool-Aid.
bandwagon, I don't know, I think.
Preston?
To our left.
You think it's going to go that way?
Yeah.
The opposite direction?
Yeah.
Why?
I don't know. Wait, Cohen not to the opposite direction? What was Cohen saying?
Cohen
Cohen's
says it's
gonna
going to go this
right.
way.
So you're
Preston says it's going to go that way.
So you're taking
I'm going
that.
to take this and I'm going to move it in this direction.
Oh, no, it's
Yeah, it's going left.
it's
Sorry.
going left. Yeah, no.
So I'm going to be like this, okay? I'm going to move it this way, right?
Yeah.
So I'm going to move it this way to my right. So is it going to move to the left? Is it going to move to the right, or is it just going to stay in the middle? Yeah, Sean?
Do you have a water? Isn't there a water bottle?
To the
Put a
left.
pencil.
No,
in the
no,
water bottle.
no.
Left.
To the left. So you're saying it's going to move to the left. God?
Yeah.
You're saying it's going to move to
The right.
The right, the opposite direction.
the opposite direction.
Because
Well-
of magic.
No, because the water's going to resist the change in motion.
I'll
more, so
agree
the
with
water's going to
Cohen.
push to the back.
You're on the Cohen train.
I'll go
Danny?
Cohen train.
The water goes to the back and the pipette goes to the front because it's less dense.
You don't know that.
I'm
gonna
guess I'll go right.
It's floating.
It's floating! Okay, are we ready?
We're hopping on the Cohen train.
Danny?
Cohen
I
might
said
be
right.
guys.
Me and Danny are on
I
the
have
Cohen
mental
train.
reasoning.
So it's
If-
like the Eagle train and the Maverick train. Okay.
Oh,
you
I
ready?
train this founded on.
Dang it.
Yes!
It did at the end.
Hey, at the
At
end.
the end, it went to the. That's
Well, that's
right.
because I stopped.
I just slowed down.
If I move it this way, so Cohen, give your explanation again.
So the water, because it's more dense, has more inertia,
Allegedly.
more stuff,
Allegedly.
Allegedly.
is going to resist the change in motion more than the pipette full of air, which is less dense. It's floating. So when you move it, the water wants to stay in one place more so than the pipette does. So the water moves to the back end of the flask. The pipette, being less dense, goes to the front half.
It's an excellent explanation.
Yay!
Okay.
Cheers for
Yay for
beautiful.
Cohen. So yeah, so but counterintuitively, you think it should move in the opposite direction. Like if you hang something up in your car and you
Yeah.
accelerate forward,
It goes back.
Yeah.
it goes in the opposite direction, right? That's because it's in air.
And it's more dense than the air.
Yes,
So if you put a balloon
filled with hydrogen,
in your car,
it would do the exact same thing of what we just did here.
weird.
Weird.
We should go test that in the parking lot.
No.
Yeah.
Okay.
Will gets in his truck and just
All
punches
right.
it.
Like, gun it.
So let's kind of
Go
start
back
to look
into
at some
today.
examples. All right.
That was a
So-
good backup into you.
You need this chart here that has all the different densities of the material. So
Got a back.
here I've got yonder hydrogen-filled balloon. Okay.
Density.
And then I'm going to have Hank. Okay.
Yeah, hey.
So
The bullet ball.
I've got
My
Hank.
hero.
Indeed. Funky.
and I've got the hydrogen-filled balloon. Okay? So, for the sake of argument, and it isn't horribly different, let's assume that the balloon and Hank have the same volume. Okay? For the sake of argument. They're off by a little bit, but not a whole lot. So, I've got Hank, and I've got,
Oh, I just moved the camera over to you so they can see it.
okay.
You know, zoom out
Right.
or in, whichever one this is. Yes.
So here's the question. Which one will have the greater buoyant force? Hank or the balloon? Or is it the same?
Wait. A buoyant force is
It would be
density of what it displaces. So let's say it just displaces water
Air.
times
Or air in this case.
times the volume.
the volume, which
Times
are the same, and gravity is
Yeah,
the
that's
same. So it should be the same buoyant force, right?
Same buoyant force. Okay?
That makes sense in
But
brain.
Hank falls like a rock. The balloon floats.
Falls like a balloon.
They have the same buoyant force, but
The-
it's not taking into account the mass that Hank has.
The force gravity on on Hank is way more.
It's
Yeah.
greater than the buoyant
This
force.
adds to your argument if you do this.
So it overcomes the buoyant.
That's a good point, Colin.
Yeah,
Okay.
the buoyant force acting on the balloon is enough to lift the balloon up because it has less mass. Force gravity acting on the balloon is much less than force gravity acting on Hank,
Okay.
right?
Yes.
Yay!
Yay! Owen's on a roll. He's like a butter. So here's the story.
I have no brain cells right now.
When I let go of them, is gravity going to pull on both of them?
Yes.
4 hours of sleep.
Yes.
Guess I'm good.
It
now?
will, right? Okay? Valid. But Hank has a lot of mass, right?
A lot of mass.
So that's going to create a big downward gravitational force. Okay? The upward force on Hank, that buoyant force, relative to that weight, is going to be a small value. Okay? Now, here you have the hydrogen-filled balloon. It has the exact same buoyant force as Hank does. But the gravitational force is much less than the buoyant force. Therefore, it goes up. Now, so in this situation, here's what I want you to see. So this is tied to a string. So what are the three forces acting on that balloon? In which direction do they act?
FG acting down,
FG is acting down.
then tension also acting down,
So I've got some tension action.
Force.
and then
The buoyancy force acting up.
Buoyancy force
Yeah.
acting up. Anything else?
Isn't that the
Well,
3?
That's 3. Okay? So if I were to add these two values together, what would they add up to?
the buoyancy force.
Yeah, those two together would add up to,
Oh yeah, because it's at rest. Because the tension has to.
tension is that.
The tension has to make
Now,
up the gap between. the two.
However, if I let go of it, what happens?
It goes up.
Because now you have a
Imbalanced force.
net force which is acting
Upwards.
upward, and now it's like a rocket. Okay,
Accelerates.
so if I take a piece of iron like this and I put it in the water, what's it going to do?
It's gonna
Sink.
fall to the bottom.
It's going to sink. Why?
It's more dense than the water.
Nope, it is, but
Not the exponential.
The buoyancy force is less than force gravity.
bingo. So therefore, if I let go of it, the net force is going to act
Down.
Yeah.
downward. Okay? So this ball is also made out of iron. Okay? But if I put that in there, it floats. Damn, that was just right to be wrong. Hold on. God, that
Stuck.
was just perfectly in there.
I was about to say those
Hold on.
things. I was
Yeah,
kind of surprised it
perfect
fit.
Yeah,
That's
I
right, I
was too.
tested it before.
I was too.
You should try cooling it with ice.
Heat it up, Berg.
Put some liquid nitrogen in there.
Heat up the glass.
Ooh, let's
heat
make
up the
liquid
glass.
nitrogen ice cream.
Liquid nitrogen ice cream.
Yeah, that's the thing.
Well, doesn't that just suck?
Wow.
Break it.
Bring it
Put it in
up.
a freezer.
Bring it over to the. Actually, here, I'll just bring the camera to you.
Okay, there we go.
Oh no, he got it. Never mind. It's no fun, guys. It's not funny anymore.
That couldn't have fit in there any better. It'll fit in this bowl.
It floats.
A sphere is put into a cylinder of the exact same diameter. Can you get it out?
Okay. All right. So now this dynamic changes. So this is still made out of steel, but it floats. Why?
Buoyancy force is more than force gravity, I guess. Yeah.
The average.
It's not.
density.
It's not
Hold
solid.
on, hold on.
Yeah, it would have to be not solid.
Yeah. So, the
It's. Is it the same reason that like the ships float?
Yeah.
Why do ships float?
because they're trying to
I don't know if this
displace.
is right, but I've
Because they're a
heard,
witch, and if
I-
you've ever seen Monty Python's Holy Grail, you know exactly what floats. Witches and small stone. Anyway,
they have a bunch of witches at the bottom.
So-
Bunch of witches at the bottom. hoping it-
here's the sphere, right?
Yeah.
There's this
Okay.
Now draw the 50 witches holding it up.
No. So what are the two forces acting on the sphere?
gravity and buoyant force.
Actually, put the
So
ducks on
gravity's
top
trying
also.
to pull it down,
Mm-hmm.
What? And then you put some ducks.
and the gravitation and the buoyancy force is
With birds.
acting upward, right?
Yep.
Are there any other forces involved?
No.
Neglecting the witches.
No.
That's it, right? There's no strings, right?
Switch.
Yeah.
Yep.
Okay, I got no strings,
W.
no strings attached.
For switch. Now we know.
So since it floats, what do you know about those two forces?
They
equal.
must be different.
No. Wait.
The buoyant first must be.
The
greater.
buoyant force is
They're
There's
equal.
not enough.
They're equal.
They're
It's
equal.
floating. There's
enough.
only two forces. It's in equilibrium.
yeah, it's not accelerating
No
upwards.
acceleration.
Cannot
And you only
Not
have
escape
two
velocity.
forces, so what do they have to add up to?
zero.
Zero.
It's not.
Now, if I push it down and let go of it, what does it do?
Goes
Rises
back up.
back up
Goes
to the
back up.
surface.
So why, when I push it down, do I change the gravitational force?
No.
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 You're just
You're
adding
just
those.
applying a force.
You're
downwards.
displacing more water.
Oh, so what's happening to the buoyant force?
Increases.
Increases.
So it accelerates upward because it's unbalanced. That makes sense.
Okay? So if I push it down, and if
Eureka
you look at
moment.
how
Let's
the
take off my
buoyancy
clothes and run
force
around
is
this-
calculated, and that's rho VG.
4GB.
This is the volume that isn't the total volume. Okay? It's the volume that's in a particular fluid. So when I push that down, what happens to the buoyant force?
Increases.
It increases, right? So if that increases, so this is why I have to hold this down, because as soon as I take my hand off of it, what's going to happen?
It's gonna accelerate.
It's going
upwards.
to shoot upwards. So if you've ever been swimming, and if you take it like a beach ball, okay,
And you hold it under and then you let
what
go.
happens?
And it shoots out of the water.
Why?
The body.
Because
force.
it's got a lot of buoyancy force and then
Why?
because it's displacing a lot of water and it's full of air and a little bit of plastic.
Which doesn't weigh much.
Not much at all.
So it doesn't have a lot of force gravity acting on it,
So,
but
like,
it
it's-
does have a lot of buoyancy force.
Or you
Okay.
use a bodyboard to get
So it's
uppercutted
easier to
or
like
get
submerge
uppercutted
like
as
a
it comes
human.
up.
as it
Yeah.
was.
Well, we'll talk about that in just a
You're
second.
standing with your boogie
Now-
down and it just goes.
I take this piece of wood and I put it in there and it floats, okay, if you don't believe me, okay? It floats. Now, if you notice on this water line, let me put it like this. So it sank to about 1/4 of the way down, okay? And again, if I push it down, what happens to the buoyancy force?
It increases.
It increases. I let go of it,
Returns back.
let's back up.
So
So here's what's going to be important. When things float,
Gravity.
Okay.
Volume of wood displaced will equal the
they
buoyant
float
force.
because there's only two forces, the buoyancy force and the gravitational force. So now, we're going to look at this in terms of that floating piece of wood. So here's what you've got. So you've got your buoyancy force and your gravitational force, right? So if it's going to float, what do you know about those two values?
they're equal.
They're equal. So I'm going to set the buoyancy force equal to the gravitational force. Cool with that?
Yep.
Good. Now, the buoyancy force is going to be rho v g. On the buoyancy side, do I use the density of the wood
No.
No.
or do I use the density of water?
Water.
Density of water. Okay, cool. On the volume side, do I use the volume that was submerged? Do I use the volume that was above the water? Or do I use the total volume?
Submerged.
Why?
Because that's how much water it displaces.
That's the only thing, that's what it's displacing, right? Okay? So this is going to be the volume that is submerged, not the total volume. And then I've got G, no struggles there. Now, if you look on this equation sheet, or on this chart here, over here on the densities, you've got density of wood varies greatly, somewhere between 0.3 and 0.9 times 10 to the third, okay? So I really don't know what that density is. I don't care what that density is at this point. But what I do know is that if I know the density of the wood, okay, times volume times G. Now, I'm trying to find the gravitational force. Okay, this is a logic problem. Leave this out. If I said, Will Stanley, I want you to find how much this block of wood weighs. But you can't use a scale, but what could you do? If you knew the density.
Like
the density.
Eureka.
Oh, you.
No.
Eureka! That means we take off all the clothes
Didn't
around
he-
the
wasn't he
school.
using-
Shut up. That's so disturbing.
Wasn't that like he was trying to? he
It
needed
was.
a-
It was a golden crown.
Yeah. It's to say, did you just do
That's
that?
not the idea.
Okay.
Will Stanley,
Yes.
let's say that you know the density of this wood is
Oh, it's so
0.5
sad.
times 10 to the third kilograms per cubic meter.
Eureka would have been.
How could you find the mass of this
You multiply by the volume.
volume? So to find this weight of the wood, I need the density of the wood. Now, in this situation, when I float it, would I use the entire volume, the volume that's below or the volume that's above?
Volume below water line when it floats. Oh, for the FG?
Yes.
Oh, yeah, the entire volume then.
Yeah, that would be the entire volume, because the entire volume is what's creating the mass, right? So this is going to be the entire volume of the wood times G. So what's going to happen to the G?
They're going to cancel out.
G's gonna cancel out. Okay? Now, I wanna do a little bit of hocus pocus. Okay? A little bit of hocus pocus.
Enter yourself in.
Which is the bigger value, the density of the water or the density of the piece of wood?
Density of the piece of wood.
Is bigger?
Then the density of water.
No.
No,
I think water is probably more dense.
Water's more dense, right?
but it's a liquid.
Like think of fish tank
I
of
feel like
fish
solids
tank of
would-
wood versus a fish tank of water.
You could also just
Yeah,
look
fair
at
enough.
this sheet and it also
And then
says,
yeah, also the water would weigh more. That makes sense. That makes sense now. I had to think about that one for a little bit.
We're good?
Yeah, the 4 hours of sleep is not helping.
Glass of water
So,
is a glass of wood.
I'm gonna take
I mean,
the
even
density
ice
of the
is
wood,
denser than
right?
wood.
And divide that by the density of the water. Will that give me a number bigger than 1 or less than 1?
Less than one.
Less than 1. Now, I'm gonna do the same thing. I'm gonna take the volume that's submerged and divide that by the total volume of the block of wood. Will that get me a number less than 1?
Yes.
Yes, because I only have a portion of this that's submerged, right?
Mm-hmm.
True?
And the entirety.
And the entirety of the volume. Do you think these two numbers are going to be equal?
Sure, why not?
They should be.
There's an equality sign in between. Okay, last time I checked, the math that I studied anyway, that means they're the same number.
Sure.
That could have changed, I'm not sure. It's this new
If they
math.
did it equal.
Now in
That's
new
a
math that
weird.
means parallel.
Now,
No, you're looking at it. Simon.
could you estimate, since that line was like right here, could you estimate this side over here?
Probably would.
Yeah. A quarter of the volume.
Maybe 25%. Okay? So about 25% of the block of wood was below the water line.
Oh, and
So therefore, what do you think you know about the density of the wood relative to the density of the water?
less than
Should be about
25%.
25%.
About 25% density of water, and again, on here with your liquids, you have two different densities. You have density of water, and you have the density of seawater or salt water, okay? Salt water is more dense, okay? So guess what? What do you think the density of that block of wood is gonna be about? 25% of
Fresh
1,000,
yeah.
which would be about
point.
250 kilograms per
meter cube.
cubic meter. Colin, do you swim?
Yes.
Okay. So imagine Colin is floating in the water. When you float, rough estimate, you're floating. Roughly, what percentage of your body is below the water line?
Depends how much I breathe in.
Ballpark. Do not complicate this. I just want a number.
Like 60.
Okay? So therefore, if 60% of your body is below the water line, what's the average density of your body then?
650 kilograms.
If it's 60%, density of water is 1,000. Your density is about 600 kilograms per cubic meter.
Do you know what the actual density of people are?
Now it varies, like depending on how much air you've taken in, and then you get muscle versus fat.
Yeah.
I don't stay above the water
Anyway,
very well.
so-
I have completely full lungs.
Now,
I can float. Right?
why is it easier to float in the ocean than it is in fresh water?
Because there's more stuff in the ocean.
Yeah, salt and
Salt water is
So it's got like more
denser.
mass.
Whoa,
more dense.
Stanley, you just said it.
Salt water is denser.
Salt water is denser. So if you go to float in the water, so it's still gonna be 25%, but then it's gonna be 25% of a bigger number, okay? So that's why it's easier to float in salt water than it is in fresh water. Now, if you ever become like a captain of a boat, and you're transitioning from the ocean into like a freshwater river system. So when you take that boat from salt water into fresh water, because that fresh water is going to be more dense, Okay, see, the fresh water is less dense. What's gonna happen to your boat?
It'll sit
It'll
lower.
sit lower.
It'll sit a little bit lower, okay? Now, but the reverse happens. If you're going from fresh water into salt water, what's gonna happen?
You're gonna
Rise up a little
It's
bit.
gonna rise up a little bit. So if you're going underneath bridges and you have a relatively tall ship, you need to keep track of, wow, am I in fresh water or I'm in salt water? Because you might clear a bridge
put on a sticky
in
note.
fresh water, but you might not clear it in salt water. Okay? Cool with that.
Don't cruise ships have like a line, like at somewhere they have like a line on them where it
I would hope.
like for the different like temperatures and or like hot or cold water and then salt and fresh water.
Okay.
Oh, cool.
So-
Actually, that is.
We got this. Our old handy dandy Newton scale.
Well, you do just know.
So, I've got this.
I've never been on a cruise.
Neither have I. My mom can't do the rocking motion at all.
Me too.
Okay? So this is a chunk of iron that weighs 2.57 newtons. Okay? Now, is that a true reading of the weight of that iron?
No,
Why?
it's the tension of the
No.
string. Is that a true reading of
Is
the
that chunk of iron in a fluid?
Yes.
Yeah.
Oh.
Yes.
Oh.
Oh, I also understand now. Okay. There's
Because
still a
what's
little
the
buoyancy
fluid that it's
force.
displacing?
Air.
Air molecules.
Air is fluid because I forget that's a thing.
Mm-hmm.
I forget air is
So
called a
there's still a
fluid.
That
little
air is
bit
a
of
thing? That
buoyancy
air is a
force.
fluid?
I forget that air is a fluid.
Birds are the fish
So
of the air.
why can't Colin float in air?
He's dense.
He's more dense than.
Air.
It's too thick.
And I haven't
Right?
tried hard enough.
So if Colin tries to, if we lift Colin up
Yeah.
and we let go of him,
Force switch.
technically there's a little bit of buoyant force created by
Air.
the air.
So I'll be fine.
Yeah.
Yeah,
Force switch.
or not so much.
Perfectly.
Now, but if we do that in water and we let go of Colin, what's going to happen?
You gotta float.
He's going to float.
I mean, depending on.
In both situations, this is the same gravitational force acting down.
Yes.
But different at Facebook.
What?
Voice
Facebook.
FB. FB.
Did you just say different Facebook?
Yeah,
Different
voice
Facebook.
void, Facebook.
Okay. Now, here's what I'm going to do. I'm going to take that iron, okay, which in this situation is weighing all of, like, what did we say, 2.5?
We said
It's gotten
2.57, but it's gotten heavier over the
Okay,
time.
it's gotten heavier. So now, what I'm going to do is that I'm going to lower this down till it's about half submerged in the water.
Oh.
So what should happen to the reading on
It'll go lower.
the
It should
scale?
lessen.
It should decrease.
Go down. It should differ. It should change and be
I
new.
hate you.
I hate myself too. Don't worry.
So, the reading on the scale is now 2.44.
Because the water buoyancy force is also acting up now.
Okay, now,
More buoyancy.
so
Just a little bit of water.
you've got a 3-force system, right?
Yes.
So, what are the forces acting on the block?
The
Facebook.
FG.
Now, what's your... So you got it like this, right?
Up.
True?
Yep.
Yeah.
Fact check status true.
Gravity.
So, you got gravity acting down,
Tension.
acting
Up.
up,
Also down.
and you've got
Force buoyancy
that's
acting
gravity.
up.
That's gravity. And then you have Facebook.
Yeah.
Facebook.
forced buoyancy acting upward.
And they all balance.
And they add up to
Zero.
zero.
4.
Okay?
4.
So, the other option is that the water acts to shield the effects of gravity. Water is an anti-grav, like gravity can't penetrate as well through.
I mean,
Water.
definitely consider that.
Why not?
It's a valid option,
Yeah.
right?
Occam's razor.
You put anything in water, what's it gonna do? Weigh less or weigh more?
Way less.
Less.
It's gonna weigh less. No matter what, you put something in water, it's going to weigh less. Maybe just gravity is like opaque to a gravitational field.
So weight loss plan, get rid of the atmosphere.
Well, let's talk about that.
Well, atmosphere.
No,
would
no,
have,
no.
atmosphere would have buoyant
So,
force, so you'd be
You
heavier.
stand on a bathroom scale,
Did all that for nothing.
and let's say it's reading, I don't know, 180 pounds. Okay? And you go, wow, the doc says I need to lose weight.
Natural gas increases.
Cut off
So
the
when
finger
you
atmosphere.
stand there, the buoyant force is created by air, which isn't very much. So imagine that you could take that bathroom scale and put it at the bottom of a swimming pool and then stand on it.
Oh, now we're talking.
What would happen to the reading on the scale?
It would go down.
It would go down.
Why is his back longer than his legs? His legs are just like
Back off. Okay?
hitting up there.
So
What's hitting the scale?
what would happen? Now, did you actually lose weight?
No.
I mean,
No.
you can lose mass.
But no. But why did the reading on the scale go down? What do you have?
Force buoyant.
More of a buoyant force.
More Facebook
Okay.
mass.
Now, on this one, I'm going to completely submerge the iron block. If I completely submerge the iron block, what will happen to the reading on the scale? Will it go to zero?
No,
Why not, Will?
because the cube is still denser than the water.
Because it's still.
So like
it's,
the FG is still greater than the FB,
Because you're adding FB
So the
and.
net.
Yeah.
and then the tension will balance it out.
Okay?
The
So if
tension
I
is
lower this
balancing.
down,
Yes.
it does decrease, but it drops to 2.24. Okay? So the initial value was 2.67. Then it was half submerged and it was 2.44. And now we're all the way down to 2.24 newtons. Okay? So if you were to draw a graph, and this is the volume that's submerged, and this is the tension on the string, what would that graph look like? So this is the volume that's submerged. So if you have no volume that's submerged, that's going to be your maximum value in this case of 2.67 newtons. True?
True.
Yeah.
So when it's half submerged, what's going to happen? It's going to drop down to
Half.
2.44. When it's fully submerged, it's going to be down to. So as more and more of it is submerged, the tension is going to become smaller. If I did that same graph of volume submerged versus gravitational force, what would happen? Colin,
Can you repeat the question?
if I did that same graph for volume submerged but gravitational force,
Oh, gravitational force is the same all the time.
yeah, that would just stay the same, right? Because that's not going to change, because that's just a fixed value, okay?
Wait, so are those supposed to be swapped then? The
Huh?
tension and volume submerged. Is tension supposed to be on the y-axis?
It doesn't make any difference. Where, I mean, I could have put tension over there, I could have put, doesn't make, I just picked it that way, okay?
You're not allowed.
Cool with that.
You go to jail.
It doesn't, yes, like, no, there's no way you can do this. So, here's the story. So when you look at a system, Here's your three possibilities, okay? If it floats, there's only two forces involved, which is gonna be what?
Facebook.
FG and
Facebook.
Facebook. That's it. If it's submerged, but the gravitational force is greater than the buoyant force, you need a upward force. If the buoyant force is bigger than the gravitational force, you need a string. So those are the three ways that any buoyancy problem is going to play out. Okay? All right, so stop you on the camera.
With the buoyant